All right. Good morning, folks. Let me go ahead and let me get the timer started here so I can stay on track. Um, well, hopefully, you were able to watch, you were able to understand the material on the video yesterday. Please make sure then, like I said, if you aren't quite sure, stick around after I take roll and ask your questions. Okay. Make sure you also remember that I'm available during our class time. So as you watch the video, if a question does come up and you're not quite sure, if a question does come up and you're not quite sure how to get the answer, pause the video, come back and get some clarification on it, and then go back and finish watching the video. Okay, so please make sure you make use of the opportunity to ask questions of me, and so come by and get your questions asked. If not, though, like I said, if not today, make sure tomorrow. Let's see, no, tomorrow will be Wednesday. Yeah, so tomorrow, stop on by after examine and get your questions answered, and then go ahead and watch the video for tomorrow. Okay, so do get your questions answered, you guys. Don't hesitate to come by and get your questions answered. Okay. Uh, the other thing, I also want to make sure if you have checked on Classroom, you'll see then that there's a couple new posts. One that I posted the homework for the new edition for chapter 7 here, and I've also posted the material for chapter 9 because what I will be doing after we finish talking about how these ions form and how the compounds form, we're going to jump to chapter 9 and we're going to talk about how we name ionic compounds. And I'll be doing that with chapter 8 as well. So I will be combining uh, parts of chapter 9 into chapter 7. So I'll be talking about 9.1 as well. And then when we get to chapter 8 and we talk about covalent compounds, I'll be incorporating in 9.2. And then we'll finish up after with chapter 8. We'll finish up with the last two sections of chapter 9. So we will be incorporating chapter 9 into into chapter 7, and then we'll be incorporating other parts of chapter 9 into chapter 8. So please make sure you keep that in mind. The exam then for each chapter will also incorporate parts of chapter 9. And then what I'll do then is I'll finish up with the last couple sections of chapter 9 involving naming acids and bases. And then we'll talk about the two laws at the end of chapter 9. And then we'll probably have just a little quiz on that. Okay, so please make sure you take a look at the chapter 9 material, and we'll hopefully start the naming part in let's see, Wednesday, Thursday, hopefully Thursday. So with that said, then I would highly suggest that you memorize. So the table from your book in chapter 9, the table of polyatomic ions. Let me go ahead and refer to you to that again, so that it will be on page. I think it's on page 250. Let's see here. I can never remember. So yeah, on page 257. So this is for the old edition. I can't remember what the page it's on in the new edition, but it is table 9.3 in both the old and the new edition. So please make sure then that you memorize that table, and that'll help you with the naming of the polyatomic ions. Okay, so those are the two announcements I wanted to make. So please make sure then that you asked about if you need any clarification about how we will incorporate chapter 9 into the new material, into the material for chapter 7 and chapter 8. Okay. All right. So with that said, then let's pick up where we left off with yesterday. So I'm going to go ahead and I'm going to open up a whiteboard here. I'm going to share the whiteboard with you first, and then and then we'll start from there. Okay. So let me go ahead over. Okay, so we were talking about how the cations form. We were talking about how cations form from metal atoms. And so make sure you keep in mind then that it's the metal atoms. So make sure you remember where the metal atoms are found and what we consider the metal atoms. But the metal atoms then will lose electrons in order to become cations. And the reason why they lose electrons for some of the metal atoms is because they can, at that point then, obtain a more stable electron configuration. And that more stable electron configuration resembles those of the noble gases. And so remember with the noble gases, and the reason why they are stable is because they have 8 electrons in their valence shell. So if we take a metal atom, let's take an example here of gallium. Okay? So let's take a look at gallium as an example here, and this is use this as a review. So gallium is using the Lewis dot structure for gallium. Gallium is a 3A metal, so we know then that gallium will have 3 valence electrons if we can draw the Lewis dot structure that way. Okay? The electron configuration for gallium, I'm going to write out the noble gas configuration for gallium. That's going to be argon. Okay? And then we have then 4s2, 3d10, 4p4s2, sorry, 4p1. Okay, and so our 3 valence electrons are here. There's the pair, and there's the lone electron right there. Okay, so gallium then has 3 valence electrons. It's in group 3A, and so if you notice here, then what gallium can do, and if we keep this in mind, then gallium can lose these 3 electrons here in order to obtain an electron configuration that resembles that of argon. Okay. And so let's go ahead, let's use this here to help us out. And I want to go ahead and I want to use this to get you to see one thing here that will allow us to segue into our discussion of the transition metals. Okay? All right, so gallium's going to lose its 3 electrons. And what we see gallium doing then is it will gain then a charge of 3+, okay, because of these 3 electrons. And what it's left with then is going to be argon, okay, and 3d10. Argon 3d10, that's what we have for gallium. Now, this isn't quite a noble gas, and let's make sure we keep this in mind. Okay, so noble gas then is that it would only be argon. Now, what we have here then is also a stable situation where we have a completely filled d orbital. And so we referred to this situation here yesterday then as a pseudo noble gas configuration, because it's not quite the noble gas configuration, because if it did, we wouldn't have these 10 electrons right here. And the reason why this is going to be stable then is because the stability comes from a completely filled d orbital, and we talked about this as well. So completely filled d orbitals will also provide a certain amount of stability, as well as half-filled d orbitals, half-filled d orbitals. And this is what we refer to then as the criteria to define that a pseudo noble gas configuration. We either have a completely filled, so it'll be a completely filled d orbital or a half-filled d orbital. In either case, then we have then a stable atom, a more stable atom than if it weren't half-filled. Okay, and so we were able to see then yesterday when we were talking about this, we were able to see then that if we take an atom like iron. Okay, so let's take a look at iron. Oops, sorry. Let's take a look at iron really quickly here. So if we take a look at iron, iron then also has a configuration that's going to be similar to this. So let's go ahead and let's take a look at it. Okay, so we left off with iron yesterday. Okay, so iron then we said then what has the electron configuration of argon. Okay, and we have then 4s2 and 3d6. 2, 3, 4, 5, 6. Okay, so 3d6. Okay, so that's the electron configuration for iron. And so we draw the Lewis dot structure for iron then, 2 electrons based on these 2 valence electrons right there. Okay. Now, with iron then, when we take a look at this, and we saw this already, if it were to lose those 2 electrons from the valence shell, so we were talking about this yesterday, if it loses those 2 electrons from the valence shell, then this is what we end up having. So if we lose these 2 electrons here, we will gain an atom. So if it loses the 2 valence electrons, okay, we will have an atom that was going to be an iron 2+. And with this electron configuration, we have argon 3d6. Okay, so with iron, then let's just make sure you understand that when we take a look at this, the reason why iron is going to have a 2+ is because then if we take a look at the composition of iron, it's going to be 26 protons here. And in this case, then we'll have 26 electrons. Okay? So in this case, when it becomes the iron cation, we can have 26 protons. Okay? But we only have 24 electrons, and thus we have the +2 charge right there that accounts then for this cation, the loss of the 2 electrons. Okay? All right. So in this case here, we would say then, well, if this is the case, then why can't this work? And there's an instability that comes with a partially filled d orbital. A d orbital that is partially filled, and you have 4 with 6 electrons. Okay? So we noticed it, and this is what we do, and we we have a method of being able to determine this electron configuration here. We learn it a little bit. A few of you will learn it as you go on to AP chemistry. But we use a method called photoelectron spectroscopy. Okay, and what we can do there is we can kind of study the energetics of these electrons here, and we notice then that this is not the case with iron. Then we don't have the orbital, okay, orbital with 6 electrons there. So that's not what happens. Okay? So we don't see this happening here. So that's not the case. So what does happen then? Let's take a look at what could possibly happen and what we actually see happening here. So if we take a look then at, I'm sorry, so let me go ahead and this here. Okay. So if we take a look at what does happen here, okay, let's take the alternative route here. And so we do see an atom of iron that is 2+. Okay? So understand, at the end of this process, then we do see an atom, iron 2+ does exist. This particular atom does exist. So that means then whatever this atom is, it will have 26 protons and it will still have 24 electrons. The composition of this actual atom will be exactly like this. However, in losing the 2 electrons, it's where the 2 electrons are lost that is different. Okay, so let me go ahead and write down the electron configuration for this atom, and you can see then where it's different. Okay, so this is going to be argon 4s1 3d5. Okay, so the difference then between the actual iron cation, so this is the actual iron cation. Okay, so this is the iron cation that forms. Okay. The difference between the iron cation that does form and the iron cation that does not form is that the 1 electron is going to be lost from the 4s orbital, and that is it. But then 1 electron is going to be lost from the 3d orbital. Okay, so that means then there's 1 valence electron left for this particular iron cation. Okay. And why then does iron do this? Because what we noticed here, and we saw this when we were talking about the exceptions to the Aufbau principle, remember, a half-filled d orbital. And this is where we got to remember, a half-filled d orbital imparts stability. So going back to what we see up here, a half-filled d orbital provides more stability than a partially filled d orbital that it has 6 electrons in it. Okay? So it's this that makes it stable. And this is the reason why this is the electron configuration for iron 2+. It loses 1 electron from the s orbital, 1 electron from the d orbital. And if you notice here, the electron, the composition of these 2 iron atoms are exactly the same. It's the electron configuration that is different. Okay, that's what we have right there. And so this is the stable iron cation right here. Okay, so from the neutral, from the elemental iron. Okay, so from elemental iron, starting out with elemental iron here, and this does exist. Okay, from elemental iron here, okay, iron 2+ forms by losing 2 electrons, 1 from the s orbital, 1 from the d orbital. It does not lose the 2 electrons from the s orbital. It doesn't lose those 2. This is the iron cation that does form. Okay, so that's what we have right there. Okay, so make sure you keep that in mind, and please make sure with this you ask questions. Okay? And so with the iron cation here, it is stable. It is stable because it has achieved this pseudo noble gas configuration. Okay, and the pseudo noble gas configuration will either be a completely filled d orbital or a half filled d orbital. Okay? So with that said, what we see then is with these transition metals, okay, because it is possible, we can see that it can achieve another ionic state. Okay, so this is one ionic state that it could achieve. This is one ionic state that it can achieve. You can imagine them. It could still maintain this half-filled d orbital if it loses that 1 electron right there. So if the iron cation, okay, loses that 1 electron right there, okay, so it's going to lose 1 electron. It becomes this iron cation with a 3+ charge. Why? Because it will still have 26 protons, but because it lost 1 more electron here, now it only has 23 electrons. And so the electron configuration for this iron cation is going to be argon 3d5. Okay, so this is a second iron cation that can form. There's the second iron cation that can form because what it does is it loses one electron here, the last valence electron, and it's still stable. And it is still stable. So we have then two possible iron cations. And that's, we see that happen with transition metals. We don't see it happening so much. We don't actually see it at all with the representative metals, but we do see it happen with the transition metals, where they will form, where the elemental iron, where that elemental, elemental neutral form of the element can form two different ions. Okay, so we have an iron cation here with the 2+ charge, and an iron cation with the 3+ charge here. And so we have to make sure that we can distinguish the difference in the two ions, not only from their symbol here. So if you notice here, each one has a different symbol. One has an Fe with a 2+, the other has an Fe with a 3+. So these are two different ions. And they are two different ions. How do we know? Not only because of the charges on them, but also because of the composition. If you take a look at the composition of each one of these ions here, you're going to see then that they are different atoms. So this is a different atom than this atom right here. The compositions are different. And those are different from, and these two ions are different from this atom right here, because their compositions are different. Okay? They all have the same number of protons, but the number of electrons are different. So they are different atoms. And so because they're different atoms, we have to make sure then that we can name them differently as well. So not only do we have to give them different symbols, so if you notice here, elemental iron has this symbol here with 2 dots. The iron cation with a 2+ charge has 1 dot, 1 valence electron. The iron cation with a 3+ charge has no dots because it has no valence electrons left over. Okay? All right. So how do we? So the symbols are different. Okay. So how then do we indicate the difference in the name? Okay. We have to place a Roman numeral, okay, to distinguish the difference between each one of those cations. Okay. And so we refer to this iron cation as the iron Roman numeral 2, and this is iron Roman numeral 3. This is what we refer to then as the stock system. Okay, and this is part of chapter 9. Okay, and I will review this again with you when we get to that chapter. But naming it this way is we're using what's called the stock system of naming ions. Stock system for naming ions. Okay, and so we will be talking about this stock system more as we go along, but make sure you keep that in mind. That's where we get the names from. Okay? So we use a Roman numeral to indicate the charge. So if you make sure you are clear on this, this Roman numeral here, okay, this Roman numeral here corresponds to the charge on the cation. This Roman numeral here corresponds to the charge on that cation. Okay? So that's how we can distinguish the difference between the cations that form from the transition metals. So the neutral transition metal can form more than one cation. Okay. Now, is that true for all of the transition metals? No, some transition metals don't. Zinc, for example, gold, silver, they only form one type of cation, but many of the other transition metals can form multiple cations, okay? And therefore we refer to them as obtaining multiple oxidation states, but they can form multiple ions with different charges. Okay, so make sure you keep that in mind. So I'll save this for you. And so let's go ahead and let's take a look at another example. Okay, let's take a look at another example. Let's take a look at silver as an example. Okay. All right, so let's take a look at silver here, and silver, and let's go ahead and write this down. Silver is going to be krypton. Okay. And it's going to have 5s1 and 4d10. Remember, silver violates silver does not adhere to the off-bal principle, and so therefore it will have a completely filled d orbital and a half-filled s orbital. Okay, so silver then, I hope you can clearly see then what type of ion silver will form here, because if you look at it, okay, you can see then that silver already has a completely filled d orbital. It has one valence electron. And so what can silver do? Well, silver will lose that one valence electron to form then silver. Okay? And let's go ahead and let's just real quickly. Let's do the composition of silver as well. That way you can see it. So silver then is going to be 47 protons, okay, and 47 electrons. So this is going to be our elemental silver. Okay, silver in its elemental form. Okay, all right. So it loses that one electron. In losing that one electron, it's going to lose it from right here. It will not lose. It will not allow an electron to be lost from the 4d orbital because the 4d orbital is already stable. It's filled, it's stable. And so this one electron here is going to come from the half-filled s orbital here. So therefore, then this iron atom here is going to have the electron configuration of krypton 4d10, much like what we saw with gallium in my very first example. Okay, so this particular atom here will have its 47 protons because it is silver, but since it lost one electron, it's going to have 46 electrons. Therefore, it's charged and it's going to be a plus 1. Okay, so it's going to be silver 1 plus. Okay, it has a plus 1 charge. Okay, and so this silver atom is different from this one, so we refer to this one as the silver cation. Okay. All right, and so with that said, then we don't technically need to have a Roman numeral here. I guess you could. I mean, technically it's not correct, but if you put the Roman numeral here, this would be silver 1 cation. And the reason why we don't need that Roman numeral is because hopefully you can see then that this is the only cation of silver that can form. If we were to form if nature were to form a second silver cation, let's go ahead and do this. It would have to lose one or more electrons from the d orbital here, and that cannot happen. If it loses, let's say, one more electron, it has to lose it from this from the 4d orbital here. So in order to form the silver 2 plus, so in order to form this silver 2 cation, in order to form that silver 2 cation, silver would have to pull an electron or give up an electron from that d orbital, so that it will have 47 protons and 45 electrons as well. Okay. Now, that will not happen. I hope you can see why this will not happen. This cannot happen. That ion will not form because now you have an d orbital that is not completely filled. Remember, nature wants stability. And in achieving this pseudo noble gas configuration here, so this is another pseudo noble gas configuration. In obtaining that pseudo noble gas configuration, silver now has become stable. And actually, silver is already a fairly stable metal. That's why we make jewelry out of it. Okay? But the silver ion is even more stable because it has now only that completely filled d orbital. It doesn't have to worry about that. Again, the elemental silver is already a fairly stable atom. That's why we make jewelry out of silver metal. Okay, same thing holds true for gold as well. But the ion that forms from silver is even more stable than this elemental silver itself. Okay? And so therefore, that's why silver then will not form any other cation besides the silver 1 cation. Thus, we don't technically have to include that Roman numeral 1 in there. We don't have to use the stock system for it. Okay. All right. Very good. Hopefully then you can see them with these, and let me go ahead and save this for us. Okay, so let me go ahead then and let me open up. Okay. So hopefully you'll be able to see then that when we talk about these ions here, okay, the elemental iron here, and the iron 3 plus here we already can see then will form because these two electrons will be lost. Okay, so an electron from the s orbital, but also remember, we lose an electron from the d orbital first, okay, and that provides the stability there. Okay. All right. We see the same thing happening then with silver. Silver loses the s orbital electron from the s orbital, and thus this is the only electron that the only silver cation that will form. Now remember, with the iron cation, there is one other cation that forms there, and that's the iron 2 plus. And so we got to make sure that remember then that when we name these ions, we're going to use the stock system, and we'll be talking about that hopefully a little bit more Wednesday and Thursday's lecture. Okay. All right. So with that said, then what we're going to do then is let's go ahead and let me ask you to take a look at number 11 in your problem set. What I would like you to do then is let's write out the ionization reaction. Now, remember what they are asking for when they ask. I'm asking for when I ask ionization reaction. Please make sure then that you write out the Lewis dot structure for the elemental, the neutral form of the atom, and then show and then how many electrons are lost or gained. I'm sorry, how many electrons are lost, and then what I'll do is I'm going to write out the electron configurations for you as well. You don't have to do it. Just make sure then that you include the valence electrons. Okay? So go ahead, take about a couple minutes to work on number 11 here on your own piece of paper. Show me the ionization reaction for gold and for zinc, and then we'll talk about it. Okay, 2 minutes, folks. Okay. All right, let's go ahead then. Let's take a look at both of these here. So let's go ahead and let's start out with, let me go this here. Let's take a look at gold first. Okay. All right, so gold then is going to be AU. Okay, so we got gold here, and gold is very much like silver. So I'm going to go ahead then. I'm going to write out the. You don't have to do this, but I'm going to do this for you. Xenon, and it's going to be 6s1, 4f14. And 5d10. Okay, hopefully you already see something here that's going to help you with this. Okay, so the 6s1, sorry. And so therefore, there is your one valence electron right there. So you're going to write down Au with one electron, one dot, I'm sorry. All right, so with that said then, let's go ahead and take a look at how this works. Okay. Now, we're going to write out the ionization reaction here, but I do want to draw your attention to something first here, you guys, and I hope you see this. Okay. We already have our completely filled d orbital right there, so 10 electrons, but we also have here a completely filled f orbital. This makes gold extremely stable. It does not react. That's why we refer to these as inert metals. They don't react very well. They don't react very much. Actually, there's a story, and I tell the story in AP chemistry, and I'll preview it here for you. There's a story about a Nobel Prize laureate back in during World War II, and I don't want to give too much away because I do want to encourage some of you to take AP chemistry, but then it involved two famous Nobel Prize laureates in chemistry, and how they were able to devise a method to chemically melt the gold and to hide it from the Nazis. So the acid system that they came up with to get that done is extremely powerful. And so take AP chemistry, and then I'll finish up that story for you. Okay, but gold, needless to say, is a very stable metal. Okay, and it's stable because it has completely filled d orbital, and if you notice, it also has completely filled f orbital. So therefore, the one electron that's going to be lost is going to be lost from that s orbital right there. Okay, so let's go ahead then and let's take a look at how that happens. Okay, so gold then is going to lose one electron, and hopefully you see that, and it will only lose one electron. And so if we were write out let's describe the composition for gold, okay, for the elemental gold and for the gold ion that forms. So we have here then 79 protons, okay, and 79 electrons. So that's this is the composition for elemental gold. So we have our elemental gold here. Okay. All right. So it loses one electron. Okay. And hopefully you are able to recognize at this point, then hopefully you don't have to do the composition anymore to recognize this. But in losing that one electron, then it'll have a +1 charge. Why? Because it will have 79 protons, but only 78 electrons. Okay. And so therefore the electron configuration for the gold cation now. Okay, so we form the gold cation. All right, so the electron configuration for the gold cation then is going to be xenon 4f14 5d10. Okay, filled F, filled D, gold ion, the gold cation is going to be stable. Okay, and so that's what we see then for gold. And hopefully you see then that there won't be any other gold ion that form. So gold is a transition metal. And like I pointed out, many transition metals can form multiple cations, but not gold here, because in order for gold to form another cation, it would have to lose one more electron. Okay, and if it's going to lose one more electron or two more, it's going to have to lose it from a filled F and a filled D. And if it does that, it loses its stability. The stability that it gets from having a filled F and a filled D is going to be lost. And so it won't do that. This is the only gold cation that we have. And so therefore we're going to name it. I mean, you could name it as gold 1, but we don't, because it only has one, it only has one form. Okay. All right, very good. Let's go ahead and let's take a look at zinc. Okay. All right, so we have zinc then. Okay. go ahead and write down elemental zinc. So there's our elemental zinc. Okay. All right, elemental zinc. The electronic configuration for elemental zinc is going to be argon, 4s2, 3d10. Okay, 4s2, 3d10, and that's what we see with zinc. Okay. All right. So with that said, then, so zinc. Then I'm sorry. Let me go ahead and write down the composition here. We're going to have 30 protons. Elemental zinc is going to be 30 protons, 30 electrons. Okay? And so what we're going to see then is zinc. Let's go ahead and draw this here. Zinc could potentially lose one electron, and let's go ahead and do this here. Zinc can lose one electron. And we saw this happen. It can lose one electron from the 4s to form then this zinc ion here, and this is going to be the zinc, okay, cation. So that's one zinc cation. Okay, and so therefore, and hopefully you see then it's going to lose that. This one electron can be lost from the 4s, not from the 3d. Look, the 3d is completely filled, so it doesn't want to take any electrons from there. So it'll take one electron and give that away from the 4s. We get 3d10. Okay, and the composition here then it's going to be 30 protons and 29 electrons. Okay, so that's what we have with this particular zinc cation here. But hopefully you'll see then, and this is why I want you to do this. You can see that the cation can go on, this zinc cation can go on and lose another electron because it has one more electron in the 4s orbital there. Again, it won't lose an electron from the 3d. That'll ruin its stability, but it will lose an electron. It could possibly lose another electron here to form then this zinc. Okay? This zinc cation here will have 30 protons because it's still zinc, but it lost another electron, so it would only have 28 electrons. So this zinc cation will have a 2+ charge, a net 2+ charge. Hopefully you see that, folks. I haven't been doing the math for you, but hopefully you can see then this charge corresponds to the excess of protons relative to the electrons. Okay, so this is going to be a zinc 2+, and the electron configuration for this one is going to be zinc 3d10. So we have then another zinc cation here. Okay, all right. So we have two different zinc cations here. This one then would we have to indicate then that this has a Roman numeral 1 because the charge here is a +1. This would be Roman numeral 2 because the charge here is a +2. So this is the zinc 1 cation. This is the zinc 2 cation. Okay, so that's what could happen with zinc. So what we actually see then is zinc actually has only the dominant form, the most dominant form of zinc is going to be this zinc ion right here, where it loses both of those. So this is the dominant form. This is the one that you probably should familiarize yourself with. And so this is around, there's so much of this that we really don't see very much of this at all. So we don't consider that. The zinc, when we deal with zinc, we treat it as if it only forms one type of cation, and it's going to be the zinc 2+ here. So therefore, since this doesn't really, we don't really see much of that at all, we don't have to include that Roman numeral there. The zinc cation, the only zinc cation that forms is the one that has a 2+ charge, where it loses both electrons from the 4s orbital. Okay. All right, very good. So your homework for tonight, then, it'll be due on Thursday, is going to ask you to do, so it'll be set A from chapter 7 here. It's going to ask you to work on this here as well. So you have to write the ionization reactions for these cations and show how they form, and then and be able to do that. Okay, but let's continue on. Let's continue on because your homework is going to also ask you about the anions. So we've talked now about how the cations form, the positively charged atoms. We already see how those form. Metals will lose electrons in order to form these positively charged ions that we call cations. But we have a whole category of atoms that are referred to anions because those are negatively charged atoms. And so how do these negatively charged atoms form then? That's what we got to make sure we are able to address because they are they are as important because the only way that an ionic compound will form is if you have a cation coming together with an anion. And so with an anion, then, what we need to make sure we understand then is that if the cations are the ones that are the atoms that form the, if the metal atoms are the ones that form the cations, it's the non-metals that form the anions. And think about why. Think about all the non-metals. They're on the upper, they kind of occupy the upper right-hand corner of the periodic table. Therefore, the non-metals tend to be very electronegative. They tend to be electronegative. And remember, an electronegative atom is an atom that likes to have electrons. It's going to pull electrons in towards itself. So that would make sense why the nonmetals are going to be that's going to make the make up the anions. Okay? And so with these nonmetals, then they will pick up enough electrons in the same way that metals lost enough electrons in order to obtain the octet. Okay, like with the exceptions of the transition metals, nonmetals will gain enough electrons in order to achieve the octet as well. Okay, and so what I'd like to, I'm out of time here. What I'd like to do on the lecture tomorrow on Wednesday is I want to talk about this. I really want to delve into this, and we want to talk about how anions form. But do understand that the anions form for the exact same reason that the cations form. They need to achieve stability. And the way that that these atoms, these nonmetal atoms, achieve stability is by gaining enough electrons, okay, in order to obtain the electron configuration of a noble gas. And the good thing, excuse me, the good news for you is that with the nonmetals, there is no pseudo noble noble gas configuration. All nonmetals will gain enough electrons to obtain the noble gas configuration. So we don't have to worry about the pseudo noble gas configuration. We don't have to worry about half-filled d orbitals or completely filled d orbitals. We just need to figure out how many electrons a particular nonmetal atom will gain so that it will get the 8 valence electrons that it needs to become stable. And so we'll pick up with that discussion on the lecture for tomorrow. Okay. All right, folks, have a good rest of your day. And again, make sure you remember that if you have any questions, please stop by either during class today or as you're watching this video, or stop by tomorrow during office hours after the exam and get your help at that point. Okay. All right. Very good, folks. I will see you in class tomorrow. I'm sorry. I will see you in class Thursday. Okay. And then we'll continue with this discussion tomorrow in the video. Okay. All right. I'll talk to you. I'll see you soon.